Yes. So today what we're going to do is we're going to look. So previously we've looked at the affine connection and the action on vector fields. So we looked at the derivative along the x direction of a vector field W. Okay. And now what we're going to do is look at the generalization of this to say, suppose we have some tensor, okay, at the point P, or some tensor field, okay, which is over the entire manifold. We can talk about the derivative of this tensor field along the x direction, okay, at the point P. So we're going to generalize this idea of taking this affine connection or covariant derivative to derivatives on tensor fields rather than just on vector fields. Okay, so we'll start with something uh, uh, rather simple. Okay, we'll start with just defining the action on a scalar field. Okay, a scalar field F. Scalar fields are just functions on the manifold, and these are smooth functions. So F belongs to these smooth functions F of M. Okay, on the manifold. And we can define the action or the derivative on F as xf, okay, where x is this vector field, okay, and f is the scalar function. And so you see that if we fed this derivative function f, the result that we get back is also a scalar function on the manifold. Okay, so if you feed it a scalar function, you get the change in that scalar function along the x direction, which is also a scalar function. Okay, so that's xf. Okay, where xf, you remember, in components was partial x mu of f. It's just this. Okay, that's what we, sorry, times x mu. Okay, where x mu are the basis coefficients. Okay, so now what we now if we define f this way, okay, the derivative of f this way, then according to our definition for this affine connection, we had this property that delta x fy, okay, we should be able to write it as so when we had defined the rule, we had written it as xf times y plus f times delta xy. This is how we define the rule. But now we can see with this definition of what we mean by the affine connection acting on a scalar function, we can write this first term as just delta x fy. Okay. So now what you see is that the action of this affine connection essentially looks like some kind of Leibniz rule or differentiation by parts, right? First, the derivative acts on f, doesn't act on y. Then the derivative acts on y, but doesn't act on f. Okay. And what is the result of this? Well, f times y is a vector. Okay, it's a scalar field times a vector field. So the product is a vector field. The derivative of that vector field is also a vector field by along the x direction is a vector field. Okay, by definition, it's the change in fy along the x direction. Similarly, what you have on the right hand side is this is a scalar function delta xf times a vector field y. Okay, so this is a vector field, and this f times again a vector field delta xy is a vector field because delta takes a vector y to another vector, which is delta xy. Okay, so this basically the whole thing on the right hand side is now a vector. So what we'd like now is to generalize this rule for arbitrary tensors. Okay, so for arbitrary tensors, if we have a tensor T1 and T2, and last time we defined the notion of a tensor product between two tensors T1 and T2. So if tensor 1 is of type Q1 R1 and tensor 2 is of type Q2 R2, then we define this notion of a tensor product T1 T2, which gives us a tensor of type Q1 plus Q2 R1 plus R2. Okay, and now what we'd like to do is define a notion of a derivative on this product tensor. Okay, the derivative on the product tensor product. Okay, and what we'd like is this definition. We have to give a definition to what we mean by this. Okay, because we've only defined this for scalars and vectors so far. We will give it a definition by saying it must satisfy one critical property, and that property is this Leibniz rule. Okay, so what we would like is that effectively it should be that when this derivative acts on a tensor product of tensors T1 and T2, it's first like it acts on tensor T1. Okay, the result of this will be a tensor of the same as the type of T1, which is a Q1 R1 tensor. And then when it acts on the, and then it doesn't act on T2. Okay, so there's a tensor product of these two. And the net result of this tensor product is this derivative of T1 is also of type T1. Okay, it's the same type of tensor as the T1 tensor, and tensor product with T2 will give you something again of type Q1 plus Q2 R1 plus R2. Okay, and similarly the second term as well will be of type Q1 plus Q2 R1 plus R2. It will be a tensor of this type. Okay, it will belong to this tensor field space. So the critical property that we demand for what we mean by the action of the affine connection on a tensor product is that it must satisfy this kind of Leibniz rule for general tensor products. Okay, so so what does delta do? Okay, so this affine connection, it takes smooth vectors, okay, smooth vector fields, that is x, that's the direction along which we're taking a derivative. And it takes tensors of type QR. Okay, so in this case, of course, we're looking at the tensor product, which is of type Q1 plus Q2 R1 plus R2. But in general, you're acting on a tensor. Okay, it doesn't have to be. You don't have to think of it as a tensor product. It acts on tensors of type QR, and it maps you to other tensors of type QR. Okay, and this tensor of type QR is in some sense defining the change along the direction x. Okay. So now with this rule, with this Leibniz rule, you can now find out, for example, what is the action of this derivative, this covariant derivative on different types of tensors. So we'll start with something very simple. We'll start with what is the action of this derivative on dual vectors. Okay, and we'll try to find that in component notation. So and then what we'll do is we'll generalize this to, once we know its action on vectors and dual vectors, then any tensor can be built up as a tensor product of many vectors. Okay, it can be built up as a tensor product of many vectors, Q vectors, times tensor product of R dual vectors. Okay, so R dual vectors. And that will give me a tensor of type QR. Okay, so if you know the action on vectors and dual vectors, then you can build up to the action on a general tensor by using the Leibniz rule. So what we'll do is we'll try to figure out what is the action first of this derivative on a dual vector. Okay. All right. So now we know that if you take a dual vector and a vector, okay, then this the tensor product of these two will be a tensor of type 1, 1. Okay, because this is of type 0, 1. This is of type 1, 0. Okay, and so the net result will be a tensor of type 1, 1. Okay, in components, if I have omega tensor V, okay, this in some basis I can express as omega mu, sorry, omega lower mu V upper nu. Okay, partial x nu tensor dx mu. Okay, so this is a tensor basis of tensors of type 1, 1, and these are the coefficients. Okay, this is how we defined what we mean by a tensor product. Okay, and you can see why it's a tensor of type 1, 1, because this feeds on a dual vector. Okay, and this feeds on a vector, and so the action of this tensor is on a vector and a dual vector, and the result is a scalar. Okay. Okay. So now you can define an operation, okay, on this tensor. Okay, so this tensor is of type 1, 1, but we defined this operation, a second operation besides tensor products last time, which is the operation of contraction. Okay, which is if you have a tensor of type QR, we define an operation of contraction of two indices to get a tensor of type Q minus 1, R minus 1. Okay, so for example, if you have a tensor like this, okay, you imagine that this vector feeds on this dual vector. Okay, so this dual vector is supplied as input, and so the result of this would be that you get omega mu. So when it feeds on this, you get a delta mu nu. Okay, and this delta mu nu, so I'll get V nu delta mu nu. And now when I take the summation, I'll just get omega mu V mu, okay, which is a scalar. Okay, and I mean, of course, these coefficients are different at different points on the manifold. Okay, so it's a scalar field. So this basically now through a contraction, I can take this tensor product and reduce it to a scalar. Okay, so that scalar is nothing but the inner product of W and V. Okay, which belongs to smooth functions, scalar functions on M. That is, it's a tensor of type 0, 0. Okay, so we started with a tensor of type 1, 1, and through a contraction, we reduced it to a tensor of type 0, 0. Okay. All right. So now, okay, now we want to define the action of this derivative on a tensor of type 0, 0, which is the contracted WV. Okay, but that's easy to do. Okay, we already know how this derivative acts on scalar functions. Okay, it just returns x of f. So it should just return x of this scalar, okay, which is that inner product of WV. Okay, but there's another way to evaluate this, okay, which is I can think of the operation of this inner product between W and V, okay, or this contraction that I do of W and V. I can take the inner product after I first act with the derivative on the 1, 1 type tensor. So first I take the derivative on a 1, 1 type tensor, and after that I contract the indices, okay, to reduce it to a tensor of type 0, 0. So in the first method, I am contracting the indices first and then acting with the derivative. In the second method, I am first acting with the derivative and then contracting the indices. Okay, and both methods should give me the same result. Okay, or at least I demand that both methods give me the same result. Now, okay, if you do this, okay, so now we can, so in the second method, so now the derivative is acting on a tensor of type 1, 1. Okay, and so this is our first method. This is our second method. So now when it's acting on a tensor of type 1, 1, okay, we'll follow the Leibniz rule. So first it acts on the dual vector, okay, and leaving the vector unchanged. Then it acts on the vector and leaves the dual vector unchanged. And the result of acting on a dual vector is a dual vector. The result of acting on a vector is a vector. Okay, and now we're going to take the inner products of these two. Okay, so we'll take this inner product and we'll take this inner product. Okay, and so now we have two different methods of evaluating exactly the same thing. Okay, of evaluating exactly this derivative. Okay. Okay, so now what we'll do is we'll just work this out in components. These two expressions, that is this one by our first method and this one by our second method, they should be the same. Okay, so now if we work them out in components, let's first work out the right hand side, which is this. Okay, so we'll work out this. So we'll call this the left hand side. We'll call this the right hand side. So the right hand side is derivative of x. Okay, w. So that is it should be some dual vector. Okay, it should be some dual vector. So we'll just write it as in components. Okay, and it should satisfy the linearity argument and so on. Okay, for delta x. So I can pull out the x mu. Okay, and I write it as delta mu w. Okay, and whatever this dual vector is, I want the newth component of that. And then I take the inner product with v, which means I take a v nu here. Okay, and similarly for the second term, here I take x mu outside, and now I'm acting with the derivative on v. Okay, this derivative we've already seen how to do it. Okay, and now I take the dot product. So the result of this is a vector. Okay, so remember that del mu, when I write this, I don't really mean it's the muth derivative of the v nu component. What we really mean is del mu on v is a vector. Find the newth component of that vector. Okay. And the newth component of this vector will involve, so in components, we had already seen that it's something like this, right? Plus gamma, nu, mu, alpha, v alpha. So it involves the sum over all components of v, not just in the new direction. Okay. So now this is a vector. Okay. And now we take the dot product of this vector with this dual vector. So we'll just write omega nu. Okay, so this vector has free index nu. So we'll dot it with, we'll take the inner product with omega, and that will give us omega nu. Okay, so this is the right hand side. Okay, and this is what we're trying to find out. We're trying to find out what is the action of a dual vector. What is the action of this derivative on a dual vector? So this is what we're solving for. Okay, and on the left hand side, we have x acting on this inner product of WV. So in other words, it's x mu partial x mu. That is the definition of how x acts on a scalar function. It's just this. And what is our scalar function? It's the dot product of W and V. Okay, so it's just W nu, V nu in components. So now what we do is we start differentiating. Okay, we just differentiate by parts. This is just regular differentiation. This is not vector differentiation. Okay, so we just do partial omega nu, partial x mu, V nu. And then we have x mu. Now I pull out the omega nu, and now this derivative over x mu acts on the V nus. Okay, so this is the left hand side. Okay, so now this equality between the left hand side and the right hand side, remember that we're just evaluating the derivative with respect to x of WV. This equality should be true for any field x, any vector field x, and any vector field v. Okay, so what we can do now is we can take so you see that this is linear in the components of x and v. Okay, because this derivative is linear in the components of v. Okay, and this derivative is linear in and this other expression on the left hand side is also linear in the components of x and v. Okay, so what that means is now we can take this should be true for any value of x and any value of v. Okay, so I can equate them. Okay, and when I equate them, yeah, okay, so sorry, so the first term here, which is this derivative partial mu v nu, this term partial mu v nu times x mu omega nu, that will cancel precisely with this term. Okay, so these two terms cancel against each other. And so now what I'm left with is I'm trying to find this quantity. Okay, this quantity will be equal to this term minus, okay, where when I take this to the right hand side and I only keep this connection, okay, the term with the connection. And so what I'll get is something like this, where the whole thing is, you can check this, okay, carefully, is multiplied by something like x mu v nu, and on this side also the whole thing is multiplied by x mu v nu. Okay, so what I have is from the first term, so you see there's x mu v nu, okay, and then I have partial omega nu x mu. And now from this connection term, okay, I have an x mu and I have a v alpha here. Okay, so what I need to do is, since this nu and alpha are actually dummy indices, maybe I'll make some space to show you this. Okay, so what I have is I have a term which looks like x mu omega nu gamma nu mu alpha v alpha. And what I'll do is this nu is summed over, the alpha is summed over. So I'll just replace this by nu. Okay, because it's just a dummy index, and I'll have to change this nu to alpha. Okay, so when I do this, this is a term like x mu v nu times w alpha gamma alpha mu nu. Okay, and now I take this over to the LHS. Okay, and so what I'm going to get is a minus sign times this gamma lambda mu nu, or I can write it as alpha, it doesn't really matter. Gamma alpha w alpha. Okay, and this is a coefficient of x mu v nu, and this is also a coefficient of x mu v nu. Now this equation should be true for any x vector field x and any vector field w, right? Any vector field v. So we started with this, and this should be true for any vector field x and any vector field v. So we can equate the coefficients of the muth component. The x is, like, for example, if we take mu is equal to 1, nu is equal to 1, we can equate the coefficient of x1 v1 on both sides. Okay, and similarly you can equate the coefficient of x0 v0. So the result of that is that we can just drop the x mu v nu and just look at the coefficients of x mu v nu. Okay, and this is the coefficient. Okay, and so you see that basically from the rule for how to take the derivative on scalars and the derivative for how to take the rule on vectors, okay, we now get a rule for how the derivative acts on dual vectors. So now we have a rule for derivative on dual vectors, okay, omega. And you see that it looks quite similar to the rule on vectors, except for one thing, there's a minus sign here, okay? And you have to be a little careful about the indices, okay? So it's gamma alpha, mu nu, omega alpha, okay? That's what shows up here. Versus if you, let me just write down again the rule for a vector. Okay, for a vector, the rule was you had gradient of mu v. If I want the nth component of this was partial v nu partial x mu plus gamma nu mu let's say alpha v alpha. Okay, so this was the difference, okay, in those between these two transformation rules. Okay. It uses the same metric coefficients. Sorry, not the metric. Sorry, it uses the same parallel transport coefficients, okay, that are used for transporting a vector. Okay, except it uses them in a different way. Okay, if you want to transport the components of a dual vector. Okay, and this gives us a rule. So this rule that we just derived is the rule for transformation of 0-1 type tensors. Okay, that is dual vectors. Okay, so. So now we have a rule for how vectors transform, which are 1-0 vectors are 1-0 tensors, and how, sorry, we have a rule for how derivatives act on 1-0 tensors, and the result of that action is a vector, and these are the components of that vector. Okay. We also have a rule for 0-1 type tensors and how how this derivative acts on these dual vectors or 0-1 type tensors. The result of that derivative acting on it also results in a 0-1 type tensor. And these are the components of that 0-1 type tensor. Okay, these are the coefficients of things like dx, dx nu. Okay.
Sir, isn't that a 0-2 tensor?
Yeah. So okay, here what we're sort of I'll discuss that. That's a good point. Okay, this looks like a 0-2 tensor. The reason is at the moment I'm thinking of mu as being a specific direction. Okay. So I'm thinking of mu as being a specific direction. You're absolutely right that I can think of this as a 0-2 type tensor, because here I'm thinking about mu as sort of, if I think about mu as arbitrary, right, that is I've not specified what the direction is, then I can think of this as a 0-2 type tensor using something like this. Okay. So you're absolutely right about that. In fact, I'll discuss this a little later. Okay. But really, you should think about it as we took the derivative along some direction x. So if I take the derivative along some direction x, then I have an x mu here. Okay, and I'll also have an x mu here. And then this is a 0-1 type tensor.
Okay, got it.
Okay, if I specify what that direction x is, then this is a 0-1 type tensor. Okay, if I specify that vector field x along which I'm taking the derivative. Okay, if I don't specify it, then you're right, then I get a 0-2 type tensor, and we'll see how to do this more rigorously. Okay, any other questions here? Okay, so now similarly, following this rule for how we, using our Leibniz rule, okay, plus now we know how this derivative acts on vectors, we know how the derivative acts on dual vectors, and now we can construct an arbitrary QR type tensor as a tensor product of Q vectors and R dual vectors. Okay, so we can construct some tensor like this, and using our Leibniz rule, we know how the derivative should act on this tensor. It should act by first acting on V1, tensor the rest of the stuff. Then it should act by acting on V2, sorry, del V2 and the rest of the stuff. Then it should act on so on, and then it should act on these dual vectors. Okay, so then it acts on the dual vectors, so it acts as del W1, tensor other stuff, plus, okay, so these are plus signs, plus um, W1 tensor del W2 and so on. Okay, so you can get the rule for the action on a generic QR type tensor, okay, by knowing the rules for how the derivative acts on a general vector and a general dual vector. Okay, so I'll let you work it out as a homework exercise. It's quite simple to do. Okay, but it's quite instructive also to get some practice with indices. Okay, so when you do this, okay, what you get is, if I want the muth, the direct derivative along the mu direction, and again, as Devashish pointed out, if I want to really think of this, I should think of it as, if I take the derivative along some x direction, then this is what I'm really evaluating. Okay, so this is del x. Okay, and so I take the derivative along some, let me just consider the basis of these derivatives along the mu direction. And now we're taking a tensor of Q of type QR. So there are Q vector-like indices and R dual vector-like indices. And now the way the derivative will act, okay, I'll just write out the answer. You can derive it using this Leibniz rule that we discussed. Okay, it'll first act by just a normal derivative, okay, acting on this tensor field. Okay, so this tensor field is a function of a point on the coordinate or a point on the manifold, which means it's coordinate dependent. Okay, so the derivative will act on this. Now for every vector-like index, okay, you will use the vector type rule, okay, which is you'll use lambda1. So you'll pull out the lambda1 into the gamma, okay, and then you'll use a mu rho. Rho is now your dummy index. Okay, this mu is the same mu that's over here. This rho is a dummy index, and you'll replace the lambda1 in this tensor by that rho. Okay, so this is what I mean by the vector type rule. And similarly, you'll do that for lambda 2. Okay, you'll pull out the lambda 2 here. That will be the next term. Okay, that comes from this term. Okay, so you'll pull out the lambda 2. Okay, and you'll write lambda 1, and then you'll put the dummy index rho here, and you'll put the dummy index rho here. So you'll similarly do this for all the, and you leave all the other indices unchanged, okay, of this tensor, except for that one vector index. So you're doing this one index at a time. Okay, and now what you do is you do this, repeat this for all the vector like indices, and for the dual vector type indices, that is these ones, the R type indices, what you do is you use the dual vector rule, which is you use a minus, and you get the dummy index is upstairs now, so it's this row over here, mu, and then I pulled out the new one. Okay, so I took the new one index from here, I moved it over here, and I replaced this new one by the dummy index row. Okay, so this was the rule for dual vector transformations, and similarly now you do this for the index nu2. So I keep rho mu, and then I pull out nu2. I leave nu1 unchanged, and I put the dummy index row over here, and all the vector-like indices are unchanged here. Okay, so you see that the general tensor transformation rule is like a combination of transforming each vector index, okay, separately with this gamma, and each dual vector index separately with the gamma. Okay, and of course you must have this original derivative itself. Okay, what does this tell you? This tells you that if I have a tensor of type, so obviously I can't represent a tensor by just an arrow, but some tensor of type QR at some point. Okay, and I want the derivative along the x direction. Okay, in particular, I'm choosing x to be a basis vector. So I'm choosing it to be along some mu direction, where mu is some coordinate basis direction. I want the derivative of the tensor along this direction. Okay, the derivative of the tensor along this direction, I'm trying to find the has components, right? It has, and I'm trying to find this lambda1 through lambda q, nu1 through nu r, this component of that derivative. Okay, and that is what the right hand side of this equation is telling me. Okay, so this is the rule for tensors, and in particular we'll be interested in this rule for a 0-2 tensor. Okay, because a 0-2 tensor, we know the metric is a 0-2 tensor. So if we have a 0-2 tensor, then the rule looks like this. Okay, so it has two dual vector type indices. Okay, so what we'll do is first, of course, we'll just act with the normal derivative on g lambda mu. But then we'll have the term, this is the dual vector type rule, where we have minus gamma. Okay, remember the minus sign is critical for the dual vector type indices. Rho appears upstairs. Okay, and then I replace this lambda, okay, with this dummy index rho and mu, and I put that index lambda over here, okay, inside the connection. And similarly, I do that for the second index mu. Okay, I write gamma rho nu mu, And then G, I leave the first index unchanged and the second index I replace by this dummy index row. Okay, so this gives me the change in G, okay, the change in the components of G, okay, or the derivative of the lambda muth component. Okay, so the derivative acting on G is a tensor. It's also a tensor of type 02. Okay, again, when you think about transporting along some x nu direction, taking the derivative along some x direction. Okay, then this is a tensor of type 02. Okay, when I multiply this by x nu, and this is the component of that 02 tensor in the lambda mu component of that tensor. Okay, so you see that the only free indices are lambda and mu, okay, of this whole thing. Okay, because the nu is summed over when I take this x. Okay. Okay, any questions here about this transformation rule? Okay, so so of course you have to work through it to really familiarize yourself with this action of the derivative in components. Okay, these rules are very important. Okay, this general rule is good for you to try to remember and kind of work through. Okay, so that you can remember exactly how the indices go. Okay, so now what we're going to do is yeah, so first let me just tell you a few properties of this connection. Okay, so right now we're not yet going to look at a metric. Okay, so we still have some manifold M. Okay, on this manifold M we have added some additional structure. What is that additional structure? We said that you need to specify these connection coefficients gamma. It's only when you specify these connection coefficients gamma that it gives you a notion of how to parallelly transport a vector. Okay, it gives you a notion of how to transport a vector from one location on a curve to another. Okay, and yeah, and so now we need to know how to parallelly transport a vector from one point on a curve to another, and it's only when you specify what these coefficients gamma are that you understand how to perform this operation. So this is some additional structure that needs to be added to the manifold. Okay, you need to specify these connection coefficients, and it's only when you specify these connection coefficients and you define a notion of parallel transport can you define a derivative. Okay, because derivatives require you to compare vectors at different points. And as we've discussed before, on a manifold, there is no way to compare vectors at different points. They exist in different vector spaces. So how do you transform the vectors from one tangent space to another tangent space? Okay, the tangent space at the point P to the tangent space at the point Q. You have to define a notion of parallel transport. Okay, and it's path dependent, it's curve dependent on how you parallelly transport. Okay, but once you do it, you can define a derivative. You have a notion of parallel transport, and you can define this derivative operator. Okay, now these connection coefficients, when we define them, one thing that we did was we defined them in a particular basis. Okay, so in some particular basis, we have to specify what these coefficients are. Okay, now, however, this notion of parallel transport or the notion of this derivative, okay, of the vector, this should not depend on your coordinates, right? This notion of the derivative itself should not depend on the coordinates that I assign. Okay, or if for example, if I have a point P and this resides in two different coordinate patches, so it resides in a coordinate patch U and a coordinate patch V. Coordinate patch U is, let's say, described by some coordinates X. Coordinate patch V is described by some coordinates Y. And so I can have a basis of vectors, okay, using the y coordinates. And this basis in the y coordinates looks like this. Okay, it looks some f alphas, which are partial y alpha. Similarly, in the x coordinates, I can write these vectors as partial x mu. Okay, the point is that this delta x v is a vector field. Okay, or it's a vector at each point. Okay, on the manifold. And now what we would like to do is if we have a vector v a vector field v, okay, and a vector x at this point, okay, we'd like to understand what this derivative is. It's like, what is the change in v along the x direction? Okay, that change is a vector. Okay, this entire thing is a vector, but this vector should not depend on the choice of coordinates that we're using. There should be just one choice of what that vector is. Okay, but the way we have defined this, okay, the way we have defined this derivative is through these connection coefficients. And these connection coefficients, we had specified them in a particular coordinate system. Okay, what we would like to ensure is that if we specify the connection coefficients in this coordinate system using some gammas, or we, sorry, let me write them as mu, I'll just use nu delta here. And here, if we specify the connection coefficients in some other basis, okay, so some gamma twiddles, we denote them as twiddles, and these are the components of the gamma twiddles. Then these two connection coefficients, okay, in these two different bases, should be related in such a way that my derivative doesn't depend on which basis I'm using. Okay, that is, even though in one basis I'm getting an answer which looks like this, right, for the components. Okay, and in another basis I would get derivatives. So these are derivatives with respect to x. Okay, now I could have derivatives with respect to y. Okay. Okay, sorry. This maybe I'll write out the rules later, but the idea is that now this is some coefficient of a vector. Okay, so this is some coefficient of E alpha. Okay, so this is a coefficient of a vector, and this is this entire sum, okay, over these E alphas describes some vector. Okay, this entire derivative is a vector, and we want to know what is that vector. Okay, that vector should not depend on whether I'm using this basis, the x coordinate basis, or the y coordinate basis, which means that there should be some relation between the parallel transport coefficients expressed in this basis and the parallel transport coefficients expressed in the other basis. Okay. So what we're going to do is talk about how to get the parallel transport coefficients in one basis and relate them to the parallel transport coefficients in another basis. Okay. Okay. Now it suffices to ensure, okay, that basically this rule. Okay, so we had this rule that if you parallelly transport a basis vector, okay, then this should just be your parallel transport coefficient lambda e lambda. It should be this vector. Okay, so parallelly transporting a basis vector e beta in the e alpha direction. So this is the e alpha direction. This is the vector e beta. When I parallelly transport e beta, I get to some point which is infinitesimally far away. I will get some other vector, and I take the difference between the two, divide by the infinitesimal separation. Okay, and then what I get is the derivative, which is something like this. Okay, it's a vector which can be expressed in this way. Okay, and this is just a basis expansion. Okay, now the point is that it doesn't matter whether I calculate this in the x basis or whether I calculate this in the y basis. The answer should still be the same. Okay, the transport should, I mean, this rule should be satisfied in both the x basis and the y basis. So that is, if I use the basis f, okay, I should get this rule where these are the parallel transport coefficients expressed in the y coordinate basis. Okay, where these gamma, alpha, beta refer to a y coordinate. Okay, so it's the y gamma coordinate or the y alpha coordinate. Okay, that I'm talking about. Okay, and sorry, what I mean is, if I have coordinates y0, y1, and so on, right? When I specify gamma, I'm picking out one of these coordinates, and that's what I mean over here. Okay, by taking that component of gamma. Okay, so these are the parallel transport coefficients expressed in the y basis. These are the parallel transport coefficients expressed in the x basis. And no matter which basis I use, okay, the expression for del f should be some gamma times f. Okay, it should look like this. And that should be true in this X basis as well when I use E as the basis vectors. Okay, so the fact that these two rules must be satisfied, or that this rule is basically satisfied in any basis, that gives me a transformation rule between these basis coefficients and these basis coefficients. Okay, so they get related in some way. Okay, so now it's a bit of work to derive the relationship between them. Okay, so I'm not going to derive it here. I've written it up in the notes, and you can also look it up in Nakahara. Okay, so I will just show you the result for how these two basis coefficients are related. Okay, and we'll discuss that relationship after that. Okay. So is the idea clear that we're trying to find a relationship between these two connection coefficients expressed in different bases? Any questions at this point? Okay, so it's a bit of work to derive it, but at the end, okay, what you get is that the basis coefficient gamma twiddle, okay, this is the coefficient, sorry, the connection coefficient in the y basis. Okay, it looks like this: gamma twiddle gamma alpha beta is gamma nu mu lambda, but with this coefficient. Okay, where I'm summing over nu mu lambda. Okay, and it looks like this: partial y gamma, partial x nu, partial x mu, partial y alpha, partial x lambda, partial y beta. Okay, now if you just look at this part of the rule, okay, this looks like exactly the rule for transformation of a tensor of type 1, 2. Okay, if you have a tensor of type 1, 2, then the coefficients of that tensor are like this. And the transformation rule, so supposing I'm starting with these coefficients in some x basis, the rule to get the coefficients in some y basis, okay, okay, is that you have to transform each of, sort of write a transformation for each of these coordinates. So you have to write something like partial x alpha, partial y mu, okay? And for these lower coordinates, you have to use partial x beta, partial y nu, and partial x gamma, partial y delta. Okay, so this is the transformation rule for a tensor of type 1, 2. Okay, so the first part of this transformation looks like a tensor transformation rule, but it turns out that there's a correction to this. Okay, it's not just, it doesn't just these coefficients gamma, which are your parallel transport coefficients, okay, or the connections, these between two different bases, they don't just transform like a tensor. Okay, there is this additional correction, okay, which is partial y gamma, partial x nu, partial square x nu, partial y alpha, y beta. Okay, if you look at the first part is a linear tensor transformation rule, which means the new components of the tensor are made up of linear combinations, because at each point this is a number, okay, and this number is a coefficient of some old tensor coefficient. Okay, so what you're essentially doing is you're adding up, taking some linear combination of old tensor coefficients and reorganizing them into a new tensor, into new tensor coefficients. Okay, so this part of the transformation is tensorial, but it's also what we call homogeneous. Okay, which means if I scale my tensor, original tensor by v, okay, or this original gamma by some scaling factor, okay, s, I multiplied by some s, then if this was transforming purely like a tensor, then this would also scale linearly with s. Okay. However, what you find is that gamma does not transform just like a tensor. There is also this inhomogeneous piece. Okay, this piece that does not depend on what gamma is. Okay, in your old basis, it only depends on the change of coordinates. Okay, between x and y. Okay, it only depends on the change of coordinates between x and y. Okay, and this this second piece is called non-tensorial. Okay, it doesn't transform like a tensor. Okay, So indeed, just a specification of the coefficients, even though gamma, the way we've written it, it looks like a tensor, right? It looks like the coefficients of some 1, 2 tensor. But the way that gamma must transform in order for your parallel transport to be consistent in any basis ensures that gamma doesn't actually transform like a tensor. Okay, it has a different transformation property. So the important point is gamma is not a tensor. Okay, very important. Okay, this connection is not a tensor. It's some specification that you have to make of numbers. There is a self-consistent way to do it as long as you obey this rule, okay, when going between one coordinate system and another. But it's a choice that you have to make. So if I specify these coefficients in one basis, okay, I can get them in another basis. Okay, so we made a basis dependent choice, but once you fix the coefficients gamma in one basis, they get fixed in other basis as well, any other basis as well. Okay. So the second piece is independent of gamma, and that is what is called the inhomogeneous piece. Okay. Later, okay, I'm just making a comment. This is not at all obvious right now. Okay, is that this inhomogeneous piece is exactly what will lead to things like pseudo forces when we apply this concept of the paths along which particles move, right, in accelerated reference frames. Okay, so this understanding, this inhomogeneous piece is pretty important for. I mean, there's a lot of physics in here. Okay, but at the moment, let's not worry about it. Okay, let's not worry about the connection to physics. This is just a rule for gamma. Specifying gammas is specifying n cube numbers, where n is the dimension of the manifold. It's specifying n cube numbers at every point on the manifold. You have to make that specification in some coordinate system. Okay, but if you make it in one coordinate system, I can tell you how to translate it to another coordinate system following these rules. If you follow these rules, then the derivative of v is coordinate independent. Okay, this definition of this is it's some vector, and this vector is coordinate independent. Okay, as long as you follow this rule for transforming gamma. Okay, so what you can show is that the derivative v of some vector field w, okay, that derivative in one coordinate basis, I can express it like this. Okay, using these are derivatives using x coordinates. And another coordinate basis, I can express it using the dual vector, the transformed vector coefficients, the transformed coefficients of v and w. So v twiddle and w twiddle are the coefficients in the y basis, so they're coefficients of partial y. Okay, and similarly, v mu are coefficients of partial x when I express vectors in the x basis. And these derivatives are, this derivative with respect to alpha is partial y alpha. Okay, rather than partial x mu, as we've done over here. And these are the old connection coefficients. These are the new connection coefficients, which are related, okay, using this method. Okay, and what you can argue is, the relationship between the old vector coefficients and the new vector coefficients. Okay, and if you follow this rule, okay, for this transformation of the connection, okay, the one that we just derived, then you can convince yourself that this vector is identical to this vector. Okay, these two vectors are exactly the same. They're just expressed in different bases. One is expressed in the partial x mu basis, which is this e nus, and one is expressed in the partial y beta basis, which are the these f betas. Okay, it's the same vector expressed in two different bases. They are the same provided these connection coefficients are related to each other using this non-tensorial rule. So there's a homogeneous part which is tensorial and an inhomogeneous part which is non-tensorial. Okay, so this is the key point. So delta VW results in the same vector no matter which basis we use to evaluate it, with the caveat that as long as you ensure that when I specify the coefficients in one basis, these connection coefficients in one basis, in another basis, the transformation is related, okay, using that equation that we derived, okay, for the transformation of these connection coefficients. Okay, so so again, I'll just emphasize the point. Okay, so although it looks like you're doing something basis dependent when you specify the connection coefficients, okay, because this is a basis dependent choice for how to transport vectors. There is a way to make that choice so that in any other coordinate system, the connection coefficients that I get, okay, are related to these old connection coefficients. There's a relationship between them. That relationship is a non-tensorial transformation. And once you make that rule, okay, then this operation del VW is actually independent of the fact that you chose this in a particular coordinate system. Okay, even though you chose it in a particular coordinate system, this operation del VW gives you vectors and it gives you the same vector no matter which coordinate system you use. Okay, so it gives you a smooth vector field that is independent of any choice of basis. Okay, does this idea make sense of the basis independence of this del operation? Any questions here?
Hello, sir.
Yeah, go ahead, Tosha.
Yes, sir. Sir. So in the last equation, like if we replace gamma tilde by in terms of gamma using that equation and v tilde by the vector transformation rule, so we will get back to the earlier equation.
Yeah, so you have to replace not only you have to replace derivatives of y in terms of derivatives of x, right? Because these are just linear combinations of derivatives of x.
The
Okay.
vectors and gammas.
Sorry?
And the vectors and the gammas.
You have to replace the vectors and you have to replace the gammas, and then you'll get from this to this.
Okay, sir.
Okay. And also these f betas, these basis coefficient, I mean these basis vectors, because these basis vectors are just this partial y. Right, and E mu is partial x. So you have to replace this also by, I mean, if you go from the y basis, you have to express this in terms of the x basis. Okay. It's easy to understand why this is true, right? Because our starting point was to say that instead of looking at general vectors, we demanded this rule when v is just a particular basis vector and w is a particular basis vector. Okay, we demanded that it's just this. Okay, so our starting point was to take the rule along any basis vector directions. Okay, and we demanded that this rule must be, this defines what these connection coefficients are in any basis. And if your rule is that it must always be of this form in any, when I take, the derivative along some basis vector of some other basis vector, okay, then it basically gives you the transformation rule between the two gammas. Okay, because any of these f alphas you can now replace in terms of a linear combination, okay, of these e mu's, right? Basically partial y mu is partial x alpha partial y mu partial x alpha. Okay, so these are the basis transformation coefficients. So this is basically f mu equals partial x alpha partial y mu e alpha. Okay, so you can substitute for each of these f's using this. Okay, and that's in fact how the proof goes. Okay, so you substitute for each of these f using this, and so you substitute on this side as well. And then you demand that, so you'll get a new expression which involves derivatives with respect to some e mu and e nu, and you demand that whatever you get over here should basically be reproduce this rule. Okay, and to ensure that it does, the gamma twiddle and gamma have to be related in a certain way.
So when you write the second one, E of V with respect to E of mu, we had seen a form for a vector acting on a affine connection, right? So when if you want to write it in that form, for example, in terms of coefficients, then E mu has to be written in EV has to be written in terms of E mu, right?
Here, no. So the EV and E mu are different basis vectors. I mean, if nu and mu are independent, then these are different basis vectors. If they're the same, then they're the same basis vector. So okay, so maybe I'll just write it here. This is like saying, okay. So this is like saying, let's take del V W, okay. In general, I can write this as del V mu E mu W nu E nu, okay. And by a rule, so let's take W nu to be 1 only for one of the E nus, okay. So it's picking out some particular coefficient, okay. So what I'm just getting is just E nu then, and we'll take V mu to be 1 only for one value of mu, okay. And so that will give us E mu here, okay. So this is so now basically when I act like this, right? What we had previously written as the rule was something like this. So here we've chosen W nu equals 1 for some nu. Okay, and V mu equals 1 for some nu and 0 for others. Okay, and now what we're doing is in general, when we're taking this rule, we said that this is going to be equal to some V mu partial mu W nu plus gamma nu sorry, mu alpha W alpha E nu. Okay, so so this is what we had, and so now since W is a constant or it's 1, okay, this term doesn't appear. Okay, the derivative of it is 0, and this gamma nu mu alpha, okay, is the only term that you get, and this again, this W is 1, this V is 1, so only for that particular choice you'll get some coefficient times a basis vector. So this rule is consistent with the rule that we had written down earlier. For the derivative on a general vector.
Yes, sir. Thank you.
In fact, we had started with this rule and derived the rule for a vector. Okay, in the last class. Okay, assuming those properties of the affine connection. Okay. Yeah, so now let me come to this point that Devashish had raised earlier. So this del V W you can think of as a vector. Okay, but if I give you del W and I leave this vector V unspecified, that is, I think of it as an empty slot. Okay, then I can think of this del W with this empty slot as a tensor of type 1, 1. Okay, so what does that mean? Well, what it means is you give me a vector. Okay, if you give me a vector, I will give you back a vector. Okay, you give me a vector, I'll give you back a vector. What is the vector I will give you? Well, if you give me a vector, I will give you the vector del V W, right? Because this is a vector. So, so now that's exactly what tensors of type 1, 1 do, right? Tensors of type 1, 1, okay, if you give them if you feed them, so what does tensors of 1, 1 take? Well, they take a vector and a dual vector as inputs, okay? And if you feed a vector, then you'll get back a tensor of type 1, 0. If you feed a vector and a dual vector, then you'll get a tensor of type 0, 0. Okay, so if you don't feed the second dual vector, Okay, if you only feed a vector to a tensor of type 1, 1, then what you end up with is just a tensor of type 1, 0. Okay, that is you get back a vector. Okay, so so basically tensors of type 1, 1 map you from vectors to vectors. Okay, so this derivative with sort of an empty slot sitting here is essentially just that. Okay, if you leave unspecified what is the direction along which you're taking this derivative, then essentially you've created a tensor of type 1, 1 because you will supply a vector. That vector is the direction along which you're going to take the derivative. Okay, and the result will be this del VW. Okay, which is a vector. Which is the new vector v prime. Okay, so now I can express this tensor, okay, in some coordinate basis. Okay, so in some coordinate basis, I can now express this del w with an empty slot as del e nu. Okay, and I take so this is del e nu w, and I take the muth component of this. Okay. And I write this as, if I want to write it as a tensor of type 1, 1, I write it as partial x mu, partial tensor dx nu. Okay, so this is of type vector tensor product dual vector. So it's a tensor of type 1, 1. Okay, and this is just a number. I mean, this is just some number, right? Because this is a coefficient. Now, if you think of this, now I want to feed this quantity. So this is basically del w. And now I feed this a vector. Okay, that is, I feed it the vector v rho partial x mu, and what I wanted to return to me is del vw. Okay, so let's check that. So when I feed it this vector, okay, what does it do? Well, this dual vector acts on this. Okay, it gives me a delta nu rho. Okay, so what I get is v rho, and this nu is replaced by rho. Okay, so it gets replaced by rho. So I get e rho here, w mu partial x mu. Okay, and this quantity is nothing but equal to del. Okay, so by that rule I can push this v down here. I can write it as v rho e rho w. Okay, and I take the muth component of this partial x mu. But what is this? This is nothing but del v w. Okay, it's the derivative of v, the derivative of w along the v direction. So this v rho e rho is just v, and it's the muth component is the coefficient of the x mu direction. Okay, so this is just expressing it in a coordinate basis. In a coordinate independent way, it's just del VW. Okay, so therefore, if I think of this as a 1, 1 tensor where I leave the slot of this vector unspecified, then I can write down the components of this del W as this del E nu W mu. Okay, and in shorthand, sometimes we write this as del nu W mu. Okay, that is, it's the derivative along the new direction basis vector of the vector field W. Okay, and the muth component of that. Okay, these are actually coefficients of a tensor of type 1, 1. Okay, and once I feed the vector, once I tell you that I want to take the direction along the some vector v mu. Okay, then what you will do is just calculate v nu del nu w mu. Okay, and that will be the derivative along the vector v. Okay, so Devashish, does this answer what you had raised earlier about this being a tensor of type 1, 1?
Yes, sir.
Okay. Okay, so now just a couple of things. So given the laws of transformation of connection coefficients, okay, so we saw that connection coefficients must transform according to this law. And if you now have an arbitrary connection coefficient on the manifold, okay, then if I take my arbitrary connection coefficient, so I start with some connection coefficient and I add to it a tensor, okay, or a components of a tensor, t mu nu lambda, where t mu nu lambda are coefficients of some tensor of type 1, 2. Okay, then this new connection coefficients gamma prime mu nu lambda, okay, this is also a valid connection coefficient. Okay, this is also a valid connection coefficient. Why is it valid? Well, now if I transform to some gamma twiddle, okay, this part transforms like a tensor. So it gets subsumed in this tensorial part of the transformation. And the rest of the gamma, part of it transforms like a tensor and part of it still has this inhomogeneous part. Okay, so the transformation of gamma prime will also follow exactly the same rule as the transformation of the old gammas. Okay, so if I take my original, you give me some connection on a manifold. Okay, so you'd give me some manifold, you give me some connection. By the connection, I mean you specify these gammas, okay, in some coordinate basis, and I know how to get them in any other coordinate basis, right? It's the gamma twiddles. But now what I'm saying is, instead of taking your connection coefficient, I will generate for you a new connection coefficient, which I'll call gamma prime. And this gamma prime will be related to your gamma by the addition of this tensor. Okay, so I have a new rule for parallel transport, which is different from your rule. Okay, and the difference between our rules is that I've added this tensor to gamma. And you can show that basically then that my gamma twiddle prime, okay, would just be the same as your gamma twiddle plus I added the same tensor coefficients. Okay, it's a transformation between these two that contains the inhomogeneous part. The transformation between these two also contains the inhomogeneous part. So this is a different set of connections. This is just in one basis and this is a different basis. This is one set of connections. This is in one basis and this is another basis. But these two are inequivalent connections. Okay, they are different connections and they differ by a tensor. Okay, they differ by a tensor. So so if I have a smooth tensor field of type 1, 2, I can always, starting with one connection, I can generate for you some new connections. Okay, every time you give me a tensor, I can generate a new connection. Okay, so this is related through some tensor T, then some other tensor T prime, and so on. I can go on generating new connections on the manifold. Okay, and similarly, if you give me one connection and another connection, okay, on the manifold, then the difference between these two, okay, that must transform like a tensor of rank 1, 2. So that is, if I give you a connection on the manifold and you give me a connection on the manifold, the difference between them must transform like a tensor of rank 2. Again, this is obvious because these connection coefficients must satisfy that when I transform them to a different coordinate system. Okay, so this is mine, this is yours, okay, and this is yours transformed to, sorry, yours transformed to a different basis. Okay, and this is mine transformed to a different basis. Now, what we've seen is that the difference between gamma prime, okay, and gamma is this. There's some inhomogeneous part. The inhomogeneous part doesn't actually care about what your connection coefficients are. Okay, so it's the same whether you use my connection coefficients or your connection coefficients. You have exactly the same inhomogeneous part, which means the difference between my connection coefficients and your connection coefficients, gamma prime minus gamma, that is the same in any basis. Okay, that's the same in any basis. So the difference between my connection coefficients and your connection coefficients in one basis is the same in a different basis. Okay, because the inhomogeneous part just cancels out. Okay, and so the difference between my connection coefficient and your connection coefficient is again just going to be that tensor. Okay, I could have added any arbitrary tensor and got different connection coefficients. Okay, so on a manifold, basically the point is that once you pick one connection coefficient, all the other any other possible choice of connection coefficient that you can put is related to one default choice by adding tensors, okay, of type 1, 2. Okay, so there's one sort of basic choice or unique choice that you can make, and beyond that you can generate other choices by adding these tensors. Okay, does that make sense?
So shouldn't the difference be shouldn't there be a factor of that, like gamma prime minus gamma is equal to that factor times that difference? A 3 transformation.
Yeah, sorry. I should have been more specific. I didn't really mean this. Okay, so there's some coefficients here. There's some coefficients here. So what really happens is, and this is a tensorial transformation, right? This part is the tensorial transformation. So gamma prime twiddle minus gamma twiddle. So my new tensor, my tensor in the y basis minus your gamma, sorry, my gamma in the new basis minus your gamma in the new basis is equal to tensor transformation rule. Okay, this, okay, the difference between our tensors in the x basis. And this is just a tensor transformation rule applied to this. So what that means is that the difference between our tensors, the difference between our connections transforms like a tensor. You're absolutely right. I mean, you have these tensor transformation coefficients here.
Sir, wouldn't this be easier to see if you basically look back at the original properties that we demanded of the covariant derivative? And you can see that it's all the properties are linear except for the Leibniz rule. And luckily, in the Leibniz rule itself, you get, I mean, the grad f term is essentially cancelling out between nabla and nabla prime, let's say. Because of that, nabla minus nabla prime will always transform as a nabla minus nabla prime will eat up two vectors.
Nabla prime. What is nabla prime?
Some other different connection. So nabla is one particular connection and nabla prime is.
Good. Okay. So I define a derivative using one connection. So this is, let's say, my rule, and this is your rule. Okay. Yes, for parallel transport. Acting on V.
Sure.
The same vector.
So other I would, sir, you would actually apply it on two vectors, right? Like V and W. So you can observe that nabla minus nabla prime acting on VW actually transforms, is linear in both V and W. So it's a tensor.
Nabla minus nabla prime acting on V.
V and W, right? Because.
What do you mean by V and W?
I mean, we usually wrote V in the subscript, but we might as well write it.
I see what you mean. Like this.
Yes.
This. Okay, so according to me, this is some vector. According to you, this is a vector, but this is a different vector.
No, sir. What I'm saying is that V and W we can treat as arguments that are being supplied to this function.
Good. Yeah, so for any VW, okay, it should be true that the difference between what we are supplying, right? So del VW for me generates a vector field. Del V, your del V generates a vector field. Okay, del V on W gives a vector field. The difference between the two, therefore, should also be a vector field.
Yes, sir. And if you basically make a linear, this vector field is actually generated linearly in V as well as W.
Because a vector field which is linear, where the coefficients are linearly proportional to V and W.
No, sir. What I mean completely linear. Like this is a bilinear form that acts on vectors V and W and generates a vector field.
Yeah, so del, let's just write this. So del takes in VW and it returns for me a vector.
Yes, sir. Maybe some other name. I mean, name of the
sorry, yeah. So it returns some vector U, right? And yes, this is, I think, a good way of looking at it. And you have some other specification of what this is.
Yes, sir.
Okay.
So now if you consider the operator nabla minus nabla prime acting on V and W in the same way, you realize that the result depends now linearly both on V and W. It already depended linearly on V because of our.
Yeah, so by our rule, this was linearly proportional to the V coefficients and the W coefficients. And this was also proportional to the V coefficients and the W coefficients.
No, sir, it was not proportional to the W coefficients because of that.
Sorry, the derivative acts on W.
Right.
Yeah. So the part of the derivative
sort of subtracts out. So
that acts on W subtracts out. Yes, you're right.
So in that sense, this nabla minus nabla prime eats two vectors and transforms it linearly into another. Two vector fields and transforms it into a third vector field. And the action is linear, so it's by definition a 1-to tensor. Without referring to the transformation rules in explicit coordinates.
Yeah, I think the tricky part without going to exact coordinates is to show that this is independent of, is linear in W. right? Basically, the fact that these
term
derivatives.
Yes, sir. That term looks like V of f times W, right?
So V of f times W. What is f?
So f is the scalar multiple for W.
So the coefficients W's.
Right, right.
Yeah, but to do that, you have to go into basis, right? So without going into coordinate basis, I'm not sure. Basically, you're right that this is basically proportional to the components of VW, and these derivatives on W cancel out. But how do you see that without going to a specific basis? I mean, gammas themselves are only defined in a specific basis.
Sir, I mean, in the differential geometry course, we actually did this sort of prescription where basically we said, okay, a connection exists irrespective of the derivatives and, irrespective of the coordinates. And then you introduce coordinates and then say, okay, there are some that you associate with.
Okay. So maybe there's a better way than this, but yeah, to basically show that this is linear in V and W, right? Without resorting to coordinates.
Yes, sir.
Okay. Okay. Anyway, in any case, so basically now the point is that if you give me any connection on a manifold, okay, I can generate for you other connections by adding tensors, okay, to this connection. Okay, and that's actually the only way to generate other connections on the manifold. Okay, all of them are related through additions of tensors. Okay, but gamma by itself does not transform like a tensor. It has this inhomogeneous piece in it. Okay. Okay, so now I'll just come to one very specific thing, okay, which is the metric connection. So the idea is very simple, which is on a manifold M. Okay, now we'll take a manifold with some specific metric. Okay, so the metric is G. Okay, so this is now a metric space. On such a metric space, okay, on a manifold with a metric G, there is a preferred choice of what is this connection. Okay, so remember all these gammas are related, let's say by additions of tensors. Okay, now out of all these choices, one of them is a preferred choice. Okay, and this preferred choice is called a metric connection. Okay, so one of these tensors is preferred, and that's one of these connections, the choices of these connections is preferred, and that choice is called a metric connection. So let's get the intuitive idea of why there's one particular choice which is preferred. Okay, so the idea is something like this. Suppose you have an arbitrary curve. Okay, so I've shown here an arbitrary curve, and I've taken two arbitrary vectors u and v at this point P. Okay, so I've taken two arbitrary vectors here. And now I parallelly transport these vectors to u prime and v prime at some other point q on this curve. Okay, using this connection gamma mu nu lambda. Okay, so you give me a connection, and I'll tell you how to parallelly transport them. Okay, so you can give me a gamma on any manifold. Okay, so you give me a gamma on this manifold. Now, what I want to do is I want to choose a connection such that once I have a metric, I can define a dot product of these two vectors, right? I can define a notion of an inner product of two vectors. This is not possible if you don't have a metric on the space. Then you can only define the notion of a dot product of, or an inner product of dual vectors and vectors. But now with a metric, you can define a dot product of two vectors. And what we demand is that the connection should be such that when I parallelly transport these two vectors from here to here, okay, so here when I take their dot product, and here I take their dot product, and the dot product should not change. Okay, the dot product should not change under this parallel transport, okay, between these two vectors. That is the demand that we make. Okay, and under this assumption, there is a unique choice of what this connection should be. Okay, there's one caveat to this, which I'll come to later. Okay, but essentially there's a unique choice then for gamma under the requirement that transport of arbitrary pairs of vectors along an arbitrary curve should leave the dot product of those two vectors invariant. Okay, so so we'll choose connection coefficients gamma such that the inner product uv. Okay, now this inner product is taken using the metric at this point. Okay, and now when we parallelly transport them to this point q. Okay, so what do we mean by the inner product at this point? Well, in components you take g mu nu, u mu, v nu. This is evaluated, this is the metric coefficient at the point P, this is the vector at the point P, and this is the vector coefficients at the point P. Now what we require is that this norm is preserved under parallel transport, which means we transport u. Okay, so this is the transported u at the point Q. This is the transported v at the point P, and this is the metric of g, not transported, but just the metric of g at the point Q. Okay, and the claim is that this inner product, okay, should be the same when I parallelly transport to the point Q as it is when I evaluate the inner product at the point P. Okay. Okay, so so formally, okay, what we're saying is that the inner product, which is this, I write it as in components as g mu nu, u mu, v nu. Okay, and the condition that this is unchanged under parallel transport is that if I parallelly transport by some tangent vector, by some vector w, okay, which is where w is a tangent vector to the curve. Okay, I transport this inner product. Okay, then the transport of this inner product should give me 0. Okay, that is, there should be no change in that inner product as I move along this curve, where w is a tangent vector. Now, since this is true for arbitrary curves and arbitrary vectors, this must be satisfied for any choice of w, u, and v. Okay, it must be satisfied that under parallel transport, this is 0. Okay, and so in components, you can write the same thing, okay, by choosing basis vectors for w, basis vectors for u, basis vectors for v. And components, you write this as derivative, this derivative, okay, the covariant derivative, the muth component of this acting on this scalar quantity, which is g alpha beta, u alpha, v beta. This is the inner product. This is 0. Okay. Oh, sorry. Sorry. Maybe I should have corrected something. Okay, you're also parallelly transporting the metric, okay, from this point to this point. So you're not taking the metric at point Q, you're also transporting the metric to this point. Okay, so you parallelly transport the metric. The metric is a tensor of type 0, 2, and you have to parallelly transport that as well. So when I transport the vectors uv and the metric g prime, the inner product of any two vectors should be unchanged. Okay. Now, sorry, so this is g prime at q, where g prime q is gp parallelly transported to q. Okay. Okay. So now you demand this is true for any u, v, and any component mu. Okay. So you demand that this is 0. So in components, what you get is the derivative. So the covariant derivative. So this covariant derivative, again by the Leibniz rule, first it acts on g, doesn't act on uv. Then it acts on u, but doesn't act on gv. Then it acts on v, but doesn't act on g or u. Okay. So by definition, we've said that u is parallelly transported along the mu direction, which means that u must satisfy this property. Okay, this is the transport of u is 0. Okay, so therefore this derivative, this term vanishes. And similarly, v is also parallelly transported, so this term vanishes. Okay, so what we're really saying is just the parallel transport of g along any curve, along any arbitrary direction is 0. Okay, or sorry, this change in g, okay, along any direction, this derivative of g along any direction is 0. Okay, so what we're saying is that change in g along any direction is 0. That guarantees that the inner product will be preserved, okay, under parallel transport. So now you see that okay, here to define this derivative of g, okay, we have to use an inner product, connection. Okay, we have to use a particular choice of connection. And so we choose that connection g such that this equation is satisfied. Okay, so you give me a metric, I will choose a connection such that this equation is satisfied and so that inner products are preserved under parallel transport and under arbitrary curves. Okay, so this choice that we're making for gamma is therefore dependent on what is the metric that you give me. So if you give me a metric, I will tell you what the gamma is so that this equation is satisfied. Okay, and so this picks out a unique connection. Okay, there's one caveat about the uniqueness of this, okay, which I'll come to in a second. So we'll pick out a particular gamma remember from that family of gammas that you can pick, which are all related by tensors. Okay, which are related by tensors. We pick out one particular gamma, which we call the metric connection. Okay, because it depends on the metric that we choose on the space. Okay, so gammas, you can choose different gammas for any manifold, but once you put a metric, there is one specific choice of gamma, okay, which preserves the inner product under parallel transport. That is called a metric connection. Okay, so from now on, when we use the symbol gamma, we are referring to this specific choice, okay, of this metric connection rather than talking about a general connection. So sometimes people use different symbols. They use something like mu nu lambda to talk about the specific choice of connection. Okay, so this is a specific choice, okay, which is metric dependent. So so now, okay, in components, we've already written out what this rule is, okay, for what grad u g alpha beta is. This is a tensor of type 2, or you can really think of it as a tensor of type 0,3. Okay, just in the same rule that we applied before, right? If I leave this direction of this derivative unspecified, then it becomes a tensor of type 0,3. And we can write this out explicitly. We've written out the rule for how this derivative acts on tensors of arbitrary rank. Okay, so it's partial mu g alpha beta. Then there's one gamma here from the fact that this indices of g transform like dual vectors. So there's one dual vector type transformation on the first index, and there's a second dual vector type transformation on the second index. Okay, so this is what we mean by this derivative u of g. Okay, and you can see that it depends on the connection. And so now what we demand is that this is 0. Okay, we demand this is 0, and this should be true for any mu alpha and beta. Okay, now again, I won't go through the math, and I'll leave this for you to go through. Okay, so you basically what you do is you take cyclic permutations of these, okay, and then you form linear combinations of them in such a way that you can now solve for gamma. Okay, I'll leave the details, but okay, so essentially you solve for gamma. Okay, and there's a unique choice of gamma, except for one caveat. Okay, this unique choice comes under the assumption that when you write gamma nu alpha beta, okay, we make the assumption that this is also equal to gamma nu beta alpha. That is, we assume symmetry in the lower two indices. Okay, such a choice, you have to make this additional choice. This is not something that the metric tells you. Okay, so you make this additional choice. So such a choice gives you what is called a torsion-free connection. Okay, but once you make this choice, there is essentially one unique gamma that gets picked out. Okay, and this connection is called the metric connection. Okay, and it's of this form. So it's gamma nu alpha beta is half g nu mu. What is this g nu mu? Well, remember that g as a matrix, I can think of it as like this. G as if I think of it as a matrix, then g with upper indices is the inverse of this matrix. Okay, so I have to take the inverse of that matrix and take the components of that inverse. That is what I mean by this g nu mu. And then I have partial alpha g mu beta plus partial beta g alpha mu minus partial mu g alpha beta. So it depends on derivatives of the metric. Okay, so if the metric changes from one point in coordinates to another point, then these derivatives can be non-zero. Okay, and therefore the connection coefficients can be non-zero. Okay, so this is a very specific. So you get a unique solution under this assumption of torsion-free. Okay, and this metric is called the metric connection or the Levi-Civita connection. Okay, and there's a unique choice of this. Okay, and you can see clearly that this depends on the metric. So given a metric, I can find a connection such that this connection preserves dot products under parallel transport. Okay. All right. So so now whenever we talk about a manifold, okay, we'll give a manifold and let's say we give you a metric G. The connection that we'll talk about, the connection that we use to do parallel transports of vectors or tensors, will be the Levi-Civita connection. Okay, it's the one which is we say that this metric is, or this connection is compatible with the metric. That is, it preserves dot products. Okay, so with this you should be able to do all the assignment problems. Okay, so we're going to stop here. Okay, and hopefully so now in the assignment, when you're given a metric, you can you'll be asked to take the metric connection, okay, which is this particular connection which you have to solve for, and now you can sort of work out, given this metric connection, you can work out what the what, for example, derivatives are. You can work out things like parallel transport of vectors and so on. Okay, and in particular you can start working out things like geodesics. Okay, what are the shortest curves or the straightest lines in a particular space, okay, with a metric. So okay, so we'll stop here. Okay, you should be able to do the tutorial sheet problems now. Okay, this is kind of the last piece that you need, which is a specific connection which is metric dependent. Okay, so I urge you to go through two proofs. One is the proof of how you solve for this unique metric connection. Okay, given the rule that grad mu of g mu is 0. Okay, how does it imply that unique choice of the metric connection? That is one thing. And the other rule that that you should work out is the transformation rule. Sorry, I won't scroll up. Let me just get back to this. The other rule that you should work out is the transformation rule between two different choices of gamma. Okay, the homogeneous part and the inhomogeneous part. If I switch coordinate systems, if I have a gamma and I switch coordinate systems from x to y, what is the rule that gives me gamma twiddle in the new coordinate system? Okay, that transformation rule also you should work out. Okay, so please work through these two things. Okay, these are also problems in the tutorial sheet. Okay, to actually work out. Okay, now what I can do is, since we haven't really solved any problems, okay, I can do an extra tutorial session if some of you are interested, where I can solve a simple example. It's not exactly the tutorial problems, it's a simpler version of the tutorial problems, okay? But it should help you gain a little bit of intuition of how to apply these mathematical rules. So let me just ask now, how many of you would be interested in such a tutorial, let's say on Saturday?
Might have I do have a midsem on Saturday.
You have a midsem on Saturday. Okay. In any case, it'll be recorded, so you can view it also later if you like. Sorry, don't put your hands up. Just yeah, okay. Maybe just keep your hands up, right? If you put your hands down, then I won't know how many are interested in the tutorial. 6, 7. Okay, there's okay, sizable number of you. Does Saturday at 4 p.m. work for the tutorial? Anyone with the conflict with Saturday at 4 p.m.? Okay, if not, so what I can do is then on Saturday at 4 p.m. Sorry, what time is the midsem that you have on Saturday?
Sir, my midsem is at 6 p.m.
Sorry, when?
Yeah.
Can you repeat that again, Anish?
6 p.m.
6 p.m. Okay. Yeah, so I'm not sure if you'll be able to attend live because it might be just before your midsem, but let's say 4 to 5:30. I mean, maybe it'll only take an hour. Okay, I'm just going to work out a simple example. It's also in the notes. Okay, so you can take a look at these notes if you like, which I uploaded already, where you take a manifold R2 and you try to work out all of these things in either Cartesian coordinates or polar coordinates. And later you make the choice of metric. Okay, you assume the standard Euclidean metric on the space in Cartesian coordinates. Okay, so I'll walk through this example fully. Okay, in the tutorial for those of you who are interested. Okay, it'll give you some familiarity with how to apply these ideas. Okay, and also that after this, if you do the tutorial problems, I mean, do attempt the tutorial problems before you come to this tutorial, right? It'll really help you understand what exactly are the kind of questions that you're trying to do and how to apply these ideas. And wherever you're stuck, hopefully the discussion on Saturday will help you, get over those difficulties. Okay, any questions? All right. Okay. So let's stop here. Okay. So we've everything till here, including this metric connection. Okay, is part of the midsum. So do go through this. Okay, you will be tested on this. Okay. So so go over this. Okay, and make sure you understand these ideas. You will be allowed a formula sheet, so you don't have to remember these gigantic or horrible formulae. Either you'll be given a formula sheet, or it'll be the relevant formula will be provided to you. Okay, so don't worry too much about having to remember these big formulae. Remember the concepts. Okay, that's much more important. And do the tutorial sheet. Do the tutorial sheet. I cannot emphasize it enough. It will really help you for the midsum. Okay, all these basic ideas. I'm only going to try to test mainly these basic ideas to make sure you understand how to use the concepts that we've developed.
Sir, can we use the notation used in Carol for the indices when we're transforming the indices?
What is the notation used in Carol?
He uses like primes or tildes on the indices. He keeps the symbol same. So instead of Christoffel symbol tilde, it would be Christoffel symbol nu tilde beta tilde alpha tilde.
In a different basis, you mean?
Yeah.
Yeah, that's fine. I mean, just explain your notation if you're using something that we're not doing.
Okay.
Okay, so we'll stop here, and I'll just post a message also on Moodle. Okay, and I'll see you. Those of you who are interested, I'll see you at 4 p.m. on Saturday. For any of you who are either watching this or who can't make it to the tutorial, you can either watch the tutorial, or this actual solution that I'm going to work out is just at the end of these same lecture notes which I uploaded today. Okay, see you all then. Bye bye.
Thank you, sir.